Hello everyone. Today we will discuss about the derivation for centripetal acceleration. Before that we need to learn what is centripetal acceleration, right? So centripetal literally means center seeking. Centripetal means center seeking acceleration. When we will discuss the derivation for centripetal acceleration, we will be able to understand why it is named so. We'll get to know that its direction is towards the center of the circular path. That's why this is called as centripetal acceleration, right? Now, for understanding the meaning and the formula for the centripetal acceleration, we need to draw this circular path. Let's take this as the center. Let's take any 2 points during its circular motion. Let's take this and this. Suppose at this point the velocity with which it is moving is v1, and at this point the velocity with which it is moving is suppose v2. So this is point B during its journey. This is point A during its journey, right? And when we are talking about uniform circular motion, so if this is uniform circular motion, it is uniform circular motion actually. So in this uniform circular motion, we know that the magnitude of the velocity at every point is same. That's why we say that the speed during its circular motion journey is constant, right? Let's take this as radius. Now we know that radius is perpendicular to the tangent. We know that this direction is showing the tangential direction. At this point also, this direction of velocity is tangential. So the radius will be perpendicular at this point as well. Suppose from A to B, the angle made is delta theta. And this arc AB, this arc AB is delta S. And the chord AB, this chord AB is delta R. So I can mention here chord AB is delta R and arc AB is delta S, right? Now the line which I am going to tell you now, you have to remember it throughout your 11th and 12th, because this is a result derived from mathematics, that angle between two lines is equal to the angle between their perpendiculars. So remember this thing, angle between two lines is equal to angle between their perpendiculars. Very important relation. So now look at this figure again. If you look at this line, this line is perpendicular to this, and OB is perpendicular to this V2 direction. Yes, an angle between OA and OB must be equal to the angle between V1 and V2 direction. Then look at this angle between these two, its perpendicular is this, its perpendicular is this. So if this angle is delta theta, this angle will also be delta theta, right? If V1 is the direction of this velocity, V2 is this direction. So by triangle law, I can say that this will give me the change in velocity. I can draw this this diagram, part of the diagram separately. That this is your V1, this is your V2, then this will give you delta V, right? And this I have marked delta theta. We know that these triangles will be similar. If I mark these 3 points as C, D and E point. So this is C, D and E, right? I can write that triangle BOA, look at this, BOA is similar to triangle ECD. ECD. Why so? Look at this BOA. This is B, this is A, this is O, and this is, suppose I'm just rotating it like this. So this is your C, right? This is D, this is E. These angles are equal. This is R, and here this is magnitude of V1, that is V, right? If I'm marking this as V2 vector, so this length will give me the magnitude. So this is V, and this is also the magnitude of V2, that is V. So this is isosceles triangle, and this is also isosceles triangle. Angle is same, so these will be similar. So by similarity of triangles, I can write that the sides are also proportional. So I can write here BO upon EC is equal to AO upon CD is equal to AB upon DE. Now how much is BO? BO is R. How much is EC? V. How much is AO? Again R. How much is CD? This is also V. AB is, this is delta R, right? If we talk about this length, so this is delta R, and DE is how much? Delta V, right? Now from here I can take any two terms. So this is R upon V is equal to delta R upon delta V. If you have understood up to here, we can proceed to the next step, right? So from here, I'm rubbing this diagram now, and just one thing I want to discuss before roughing this diagram, that we know that if B is close to A, then the arc length delta S is equal to this chord length delta R. If this is clear from the figure, now I think I can rub the board, right? So from here, we can write this as equation 1, this as 2. Now I can write from 1 and 2. R upon V is equal to delta S upon delta V. I have replaced delta R by delta S. Now let's divide by delta T. So this is R upon delta T, and we are cross multiplying here. Delta V is equal to delta S upon delta T. We can apply the limits. So I am applying the limit delta T tends to 0. So here also limit delta T tends to 0. So this I can write R upon V dV by dt, because I have applied the limits. R upon V as it is, delta V upon delta T can be written as dV upon dt now, and this can be written as ds upon dt. Now this is R upon V, and dV upon dt, rate of change of linear velocity, is acceleration. This is equal to ds upon dt, that is velocity, and this acceleration becomes v square upon r, right? So this is called as centripetal acceleration. Right? So from here we have moved on to this step, and then this derivation is complete. But we need to discuss the direction part also. Now, for the direction part, we need to redraw a rough diagram of the circular motion which we had already discussed. So that rough diagram is, now we are discussing what? Direction of centripetal acceleration, right? So for this, again that same diagram. At this point the velocity is v1, at this point the velocity is v2, this is the center. So here this is a radius, this is also radius, this is perpendicular, this is perpendicular, this was delta theta, and this is also delta theta. This point I had marked A, this point I had marked B, right? Now for discussing the direction, let's consider if B is very close to A. If we have, suppose these points, A point here, you need to visualize this beta. This is not given like this in the books. So if we have these points A and B, so we have this direction of velocity v1 here and slightly different direction of v2 here. So for these close points, v1 is nearly parallel to V2. Yes. And we know that if we have this diagram, let's check another diagram. Now we know that when we had V1 this, V2 this, then we had this delta V, right? But now we have this case. This is A, this is B, very close to each other. So this is V1, this is nearly parallel. So this will be the direction of delta V. Yes or no? Difference of these. Yeah. Now we know that the radius is perpendicular to V1 and V2. So we can say that our radius will be this way. If this thing is clear, you can say that R is parallel to delta V. Yes. And we know that acceleration is delta V upon delta T. So A is along delta V. Yes or no? So we can say if R is parallel to delta V, so we can also say that R is parallel to this. And what is this? This is centripetal acceleration. So I can say that centripetal acceleration is along the radius, that is along the center. Right? That means at every point, I think I can rub that diagram now. That means at every point, the direction of the centripetal acceleration changes. That means at here, if I can say that this is the direction of acceleration here, centripetal acceleration here, here the direction of centripetal acceleration is here, here the direction of centripetal acceleration is here. So at every point, the direction of centripetal acceleration changes, right? It is along the center, towards the center of the circular path, right? So I hope you understood that how this direction of acceleration is along radius. We have considered A and B to be very close, so you can draw this diagram. That means V1 and V2 are nearly parallel. Delta V will be this way by this figure if these 2 points are close. So R is perpendicular to V1 and V2. That means R and delta V are parallel to each other. We know that acceleration is along delta V. So R is along R is along acceleration, R is along the center. So you can say that the acceleration, centripetal acceleration is along the center, right? Now this was for the uniform acceleration, uniform motion case. In uniform motion case, uniform circular motion case, the direction of the centripetal acceleration is, you can say, towards the center, right? But what if the motion is non-uniform circular motion? I'll discuss that also. So this was your centripetal acceleration. So for non-uniform circular motion, For non-uniform circular motion, we know that the speed also changes at every point, right? So here direction as well as the magnitude both change. So you can say the speed changes and direction also changes, right? So if we look at this figure beta, there will be a tangential acceleration due to the change in speed. This is called as tangential acceleration. There will be a centripetal acceleration which will be center seeking. So by applying the concept of vector addition, the resultant acceleration will be along the diagonal of these two, right? So if we look at this angle, this can be called as resultant acceleration. So this resultant acceleration will be under root of first acceleration square plus second acceleration square plus 2 into first acceleration, second acceleration cos of angle between these two. How much is the angle between AC and AT? That is centripetal and tangential acceleration. This is 90 degree. So your formula reduces to under root of AC square plus AT square. A very important result from here. For non-uniform circular motion, the resultant acceleration is not towards the center, but for uniform circular motion, the resultant acceleration, that is centripetal acceleration only, because in that case tangential acceleration is not there, that is towards the center. So for uniform circular motion, I am just writing in short, uniform circular motion A towards center, but for non-uniform, net acceleration is not towards the center. I hope this concept is very much clear to everyone. This is all for now. Thank you so much and have a nice day.